In this worked example, we'll be looking at some vector addition. Question number 1 reads, two forces with magnitudes 5.0 newtons and 12 newtons act from the same point on an object. Calculate the magnitude of the resultant force R for the forces acting 1 in opposite directions. If there is a 5 Newton force acting thusly and a 12 Newton force acting thisly, then there must be a 7 Newton force resultant. Now, it just wants the magnitude. That's the how much, 7 Newtons, that's how much. But I kind of want to, tell them the which way too. It's 7 Newtons, to the right, the way I've drawn it here. They don't really say what direction these are. They just tell us they're opposing each other. So the important thing is that we subtract them. If we were to follow the procedure that's up on the chalkboard and said, how do I add or subtract vectors? Okay. Well, if I'm adding 2 vectors, but they're in opposite directions, you kind of need step 2 up there, which says that subtracting is like adding a negative. So I can still use the rule of like start with the first vector and place them head to tail, right? And so that's the tail of the first vector. There's the head. So I'm going to take the second vector, which is this is my 5. Well, I guess that's the 12 Newton force that I put this way. So then if that's 12 Newtons this way, then I take my 5 Newton force and I put it head to tail, and so it's going to go back sort of 5 Newtons that way. Connect the tail of the first to the head of the last. And so so if this was 5 Newtons, I went back 5 Newtons, right? And I get my 7 Newtons to the right, the way that's sort of drawn. So it still works to take this vector and put it head to tail, right? So put it right there. And then you see, okay, there's my resultant R, 7 Newtons to the right. There's my 5 Newtons. Because they word it like this, they're acting from the same point. It's like there's some object, and there's a force this way and a force that way. But the way that we add them is to put them head to tail. It's kind of overkill for a problem like this where you just kind of know, oh, I have to subtract them. But the rule still works. You can place them head to tail, draw, connect the tail of the first to the head of the last. It still works to give you the solution. But we don't need to know that they're, the direction. They just ask us for the magnitude. At right angles to each other, that's a bit tougher to calculate, but not too bad. 12 Newtons this way, 5 Newtons, at right angle to it. And so we just need to calculate the resultant like this. Right, and this is going to be the square root of the sum of these squared. Using Pythagoras' theorem, 12 squared plus 5 squared equals R squared. So R will equal the square root of the sum of those squares. 144 plus 25 is 169. And the square root of 169 is 13. You've got a 13 Newton result there. So far, so good. Any questions on that? Leave it down in the comments below. It goes on to give us 2 vectors like this. Clean that up. Question? Question on any of those? Any of this? Good. All right, so now we've got an object X resting on a smooth horizontal surface. 2 horizontal forces act on X shown like this. We got a 55 Newton force applied to the right. A force of 18 Newtons is applied at an angle of 115 degrees to the direction of the 55 Newton force. So they've spelled that all out right there. And our job is to use the resolution of forces. So we talked about resolving vectors, right, in the X and Y components, or a scale diagram to give us a choice there of how we can solve this, to show that the magnitude of the resultant force acting on X is 65 Newtons. So they give us the answer is 65, the sum of those, and they want to know the angle that it's making. Determine the angle between the resultant and the 55 Newton force. And then they tell us the third force of 80 Newtons is now applied in the opposite direction to the resultant here. All right, and they give us the mass, and we want to know the acceleration. So we'll work through the first part of it, and then I'll tell you all the physics you need for that last one. All right, let's go back up to this figure here. And it's obviously not to scale. If this is 55 newtons this way and this is 18 newtons, that's not quite as strong as this. Okay, but they've drawn the vector, longer than that one, or as long. All right. Yeah, make this a bit smaller, a bit easier to work with here. So they're already drawn head to tail, right? I've got like an 18 newton this way, 55 newton that way. That's head to tail. So if I were adding these two, which is what I do, if we're summing them, we're saying they're both acting on this point, then the resultant is the sum of those two. So it's not to scale, but maybe if I drew this one only where the arrow is about that long, at least it's a little bit more to scale. So I'm just going to kind of ignore this line up here. And I'm going to connect the tail of the first to the head of the last. So the resultant is going to be something like that. Okay. So that's what it's going to look like. This 18 Newton force over here goes down and to the right. And anytime a vector doesn't go perfectly to the right or left or perfectly up or down, you can always ask yourself, well, what combination of directions is this vector? It's a combination of down and right. And resolving the vector allows you to determine, how much in each direction. So my new resultant over here, I know has a component over, okay, and it's equal to 55 newtons of over from this vector plus however much right from this vector, right? Like this 18 newtons goes down and to the right. Well, how much of it goes to the right? I need to add to my 55 over here. Right, like there's a certain component of this vector that's going to the right. Let's bring it over to the right like this much. And then the 55 Newton force, pushes it the rest of the way right. The down comes entirely from the 18 Newton force vector, right? It's like that's this component right over here. This is the hypotenuse. This is 18 newtons of force going this way, 115 degrees above the positive x-axis. I think the easiest way to work with this triangle is to calculate this angle right here, and then just kind of go from there, right? So what is the value of this angle? Let's call it, well, let's be creative this morning. Let's call it theta. I'm hearing that it's 65 degrees. And if I read your mind correctly, it's because you understand that this is a supplementary angle, right? And that these two angles will add up to 180 degrees. Those are supplementary angles. So hopefully that's correct. Yes. Yeah, all I kind of did here was I translated this vector kind of up here to this is my resultant right here, right? That's the answer. It should equal 65. They told me the answer was 65. And I've just sort of constructed the legs of this sort of hypotenuse. So I know my resultant is this vector right here. And I know that it's over and down. And I know some of the over is due to this 55 Newton force. So I just sort of drawn it like this. I'm calculating right now. Let's calculate this one. So this is going to be the x component. Let's just call it force in the x direction down here. And then this one will be like our y force. And remember, this is the 18 Newton sort of hypotenuse. So we know this angle theta right here is 65 because 115 plus 65 gives me 180, right? I got 180 degrees right here. So this side right here is adjacent to that 65 degree angle. The hypotenuse is 18. The cosine of 65 degrees relates the side adjacent, the x component of force, to the hypotenuse, 18 newtons. Multiply both sides by 18 newtons. And I can calculate that the x component of this 18 Newton force, which goes kind of down to the right, do up a handy calculating device. Over here, maybe, easier to see that. All right, so we'll take 65 and click on my trigonometry button. Cosine of that is that number, 0.422 something. If you're following along with your own calculator, you'd be able to your confidence that, yep, I got 7.6. And that is indeed correct here. So this 18 Newton force is pushing it down to the right. It's pushing it 7.6 newtons to the right. There's a total of 55 plus 7.6 newtons to the right for my result. Okay. It's easy to add things when they're in the same direction. So I have to figure out like how much of this is in the same direction as the 55 Newton force. And that's this calculation right here. The down, the y component of force is opposite this angle theta. The hypotenuse is still 18. And so here, to solve for this one, I could use the sine function. The sine of 65 degrees is opposite over hypotenuse. Right? And so this is the side opposite this angle theta for this triangle right here. So the y component of force is just 18 newtons times the sine of 65 degrees. The sine of 65 is that times and so the y component of force here is about 16.3 newtons. You could double check 16.3 squared plus 7.6 squared should equal 18 squared, right? Like this is just a check on this right triangle. I've resolved this 18 Newton force vector into y component 16.3 newtons and an x component 7.6. The way to add perpendicular components is with Pythagoras' theorem. A squared plus b squared equals c squared. And that should check out in your calculator. Let's see it for completion here. There's my 16.3 whatever. I'll just keep the whole number in the calculator. Square it plus 7.6. Remember we rounded that too, so it won't be perfect, but equals, so 323 point something. Well, that should be 18 squared, right? So if I take the square root of it, you should see a number really close to 18. Yeah, 17.996. That's close to 18. So it all checks out. Now let's solve this thing. So we know that this resultant R has a to the right component equal to, what's 55 plus 7.6? 62.6. And then the down is this guy, 16.3 newtons, right? It all came from the down component of this 18 Newton force. And so now I use Pythagoras' theorem again. 62.6 squared plus 16.3 squared equals R squared. Calculate machine. Get rid of some of this. Go from here. Maybe easy come, easy go. All right, so we've got 62.6 squared plus 16.3 squared equal to that number. Take the square root of it. And that sound means you got it correct. 65 newtons thereabouts. Right, 64.68. I always like to write it like this. R equals 64.6. I guess this was round up to 69. And then to say, and that is about equal to 65. Check. Because remember what the question said. It says, show that the resultant is 65. And you're sort of removing any doubt from the examiner's mind, like, this is how I calculated it. This was my calculator value. And indeed, I've shown that it rounds to the thing that you said it should. And so that's that. If you recall, they asked us to also determine the angle that it makes relative to this 55 Newton force. Right? That was something else they wanted us to calculate. Let's remind ourselves of that. It says use the resolution of forces or a scale diagram to show that. And that's what we did. We resolved this one. That's the resolution of forces. We constructed a new right triangle. Looking at it now, it looks kind of sloppy. You probably have it much neater in your journal. Just like this is not a triangle. This is some kind of like a jagged, sphere or something like that. Use your imagination. I'm an art teacher, not a geometry teacher, I'm a physicist. Determine the angle between the resultant force and the 55 Newton force. And so the 55 Newton force was down there, and now we want the angle that this one's making with it. Well, the 55 Newton force is just horizontal, right? So we could really just calculate this angle right here, right? Because like that's horizontal. So we're saying, well, here's a vector that goes down and to the right, just like the 18 Newton force, except for it goes a lot more to the right, you know, because we added that 55 Newton force to it. And so we need this angle that it's making right here. Let's call it phi. All right, so there's an angle phi that we need to solve for because that's the angle that the resultant makes, you know, with the 55 Newton force. We could translate this resultant, you know, down to, you know, where the 55 Newton force was. We could move the 55 Newton force up like it's here. The important thing is that it's relative to the horizontal. So you can use any trig function that you want to solve for this angle because we know everything about this triangle. We know that it has a leg equal to 62.6, a leg equal to 16.3, and a hypotenuse equal to about 65, 64.69. So I'll solve it with my favorite trig function, the tangent function. The tangent of this angle is equal to opposite over adjacent. So the opposite is 16.3. The adjacent was 62.6. And so the tangent of some angle phi equals that ratio of sides. So that angle phi equals the inverse tangent of that ratio. So to solve for the angle, you use the inverse. So if I have 16.3 over 62.6, those numbers are somewhere in there. Or something. And all right, the second key, the inverse tangent of that gives me about 14.6 degrees. So we get an angle here of 14.6 degrees. You know, you could say that 15 degrees if you wanted to. That's the angle that the resultant makes with the 55 Newton force. There's 15 degrees between them. So again, the way that I solved for this angle was 16.3 over 62.6. Inverse tangent of that solves for the angle phi, which is the angle between the resultant and the 55 Newton force. That angle phi solves like this because I can just use the legs of that right triangle where r is the hypotenuse. The last part of this as a third force of 80 newtons is now applied to x in the opposite direction to the resultant. So the resultant went like 15 degrees below horizontal that way, and it was equal to about 65, if you recall. So we're saying in the opposite direction, we've now got a vector going like this, and it's 80 newtons, they tell us. And we want to calculate the magnitude of the acceleration. In order to solve that, you're going to need arguably the most important law in physics. The sum of the forces, the net force, this capital Greek letter sigma means the sum of, you haven't seen that in math class yet. So all the forces, we add up vectors like force vectors on the left side of this. And the truth of the universe is that when there is a net force acting on an object with mass m, it's going to accelerate in the direction of that net force, according to this equation. So we can calculate the acceleration A if we know the mass of something, they've conveniently given it to us, and if we know the net force. This problem is really about working on the left side of Newton's second law. It's about vector addition, right? Adding forces. So that's like sometimes this equation, it's like, oh, I got a lot of work to do on the left side over here. Got to add a bunch of forces. The right side is not too bad. You know, sometimes we got a lot of work to do on the right side. We got to calculate acceleration or something. And then we say, okay, if something is accelerating, we know it's because a net force was acting on it. There's no exception to that. Like, that's the way the universe works. And that's why this class is awesome. We're learning all the secrets of the universe. This is how it really works. All right, so can anybody out there, who among you can calculate the net force on the left side of this equation? I heard somebody say 15. Who agrees? Who concurs? Why didn't I concur? Anybody seen that? Catch me if you can. Why didn't I concur? It is 15. There's 15 newtons of net force. I didn't have to resolve any vectors. All I did was say, I know they oppose each other. And step 2 up there says subtracting is adding the negative. Negative vector just points in the opposite direction. So there's a net force of 15 that way. Okay. Put the vectors head to tail, right? So like there's that vector. Let me add this vector to it. So I'll put it head to tail. See how it's going back 15 that way. Like 80 is bigger than 65 by 15. So I just subtract those numbers to get the net force. 15 equals 2.7 kilograms times some acceleration A. So in order to solve this, you just divide each side by 2.7. Let that be the math problem that stops you. We made it this far. So I'm getting an acceleration of about 5.6 meters per second squared. If you wanted to call this negative 15, it's like saying I'm assigning this direction as positive, and so this is negative 80. So yeah, it would be negative 15. But it's sort of arbitrary which direction you're calling positive. Like I could just as easily assign this direction as positive, and then I'd do minus 65 because it opposes it. The important thing is keeping track of like if they oppose each other, one is negative relative to the other one. So if this is negative 15 newtons, and you solved it and you got negative 5.6, then you're just saying, oh yeah, of course, it accelerates in the same direction as the net force. In this case, this way, that's the direction I assigned as negative. So the negative sign here doesn't really matter so much. You could just assign your directions the other way, keep it positive. It's not incorrect as long as you've clearly sort of assigned that direction as negative. So in my advice to you is to work with positive numbers because they're easier. So if you can like predict, hey, I know that the net force is going to be this way. Let me just make that way positive. Okay, but consistency is key. Like once you've said, okay, here's a problem where something's falling down, I'm going to make down positive. Even though the standard convention is to make like down negative, you can change that. There's no rule that says you have to. But as soon as you've decided that down is negative, you kind of need to stick with that at least for the rest of that problem. So when things move up relative to down being positive, then they're negative. The important thing is keeping track of what vectors oppose each other and making like one negative relative to the other one.